1, 2. Okay. Can you hear me? Okay. So, good afternoon, everybody. Welcome back from lunch to this session, which is called What is Bothering You? Honeypots 1. This session and the next one are organized within the context of the NOAA, Network of Affine Honeypots European Union project. And we'll be talking about the work that we have been doing in NOAA, as well as some collaborations that we have in NOAA. So the first talk will be titled Honey at Home, the Eyes and Ears of the NOAA project. It will be given by Spiros Adonatos, Technical Coordinator of NOAA, and he's affiliated with ICS Forth. Spiros.
Hi, thank you for your introduction. I come from Crete, the southest island of Europe, and I'm going to talk to you about Honey at Home, the eyes and ears of the NOAA project. This is a brief outline of my talk. First, we will discuss about the motivation behind our approach, the Honey at Home tool and its architecture, the challenges we faced, and finally some summary and conclusions. Before I enter the details of Honey at Home, I would like to say a few words about NOAA. It's the Network of Affine Honeypots. It's a 3-year project that will end this year, and the goal of NOAA project is to develop an infrastructure to detect and countermeasure cyber attacks. So we want to provide an early warning of attacks happening on the internet and gather as much information as we can, analyze it, and propose defense measures. For more information, you can visit the URL of NOAA. So, NOAA is about honeypots, and the motivation behind using honeypots is that monitoring unused IP addresses usually yields to interesting results. And we use honeypot as a tool to improve our network security. One problem with honeypots is that they are hard to install and very hard to configure and maintain them. It needs a lot of human effort, especially for the maintenance part. But honeypots have shown that the more address space we monitor, the more effective the results are. So we want to monitor as much space as we can, but we do not want this space to be static, because monitoring static address space is vulnerable to blacklisting. So attackers can know that we monitor this block of address space, blacklist our space, and then we become blind. So for those who are not very familiar with honeypots, are computer systems that actually monitor unused address spaces, addresses that are not used by real users. So we can see honeypots as machines that are very closely monitored. They run virtualized software. They run usually inside virtual machines, and they can detect any known and unknown attacks. So before we start with the Honey at Home tool, there are some facts that we took into consideration. One fact is that there is a lot of unused IP address space. For example, in our local university and in Forth, we have an underutilization, so we use less than 40% of our address space. There is also some known examples. For example, UCSD that has allocated a /8, but only a few thousand IP addresses are used. And apart from our organization, and there are some other private companies, public domain bodies, and even home users that contribute to the monitoring of unused IP address space. Last but not least, there are the NAT-based home networks. Every ADSL or cable user has some unused IP address space. What we try to do is that we want to empower people to set up honeypots. We want to help them improve both their security and the global network security. So we want to provide them with a tool that has minimal installation overhead and nearly zero runtime overhead. And it is appropriate both for home users and organizations. So we have the tool that for those who want to contribute but do not have the technical knowledge, because not everybody knows how to run honeypots and how to maintain them. So our approach is called Honey at Home. And Honey at Home is a tool that enables users to set up a virtual honeypot at their home computers. It's a very simple tool, doesn't need any configuration. You just install and run it. And we have implemented a Honey at Home for both Linux and Windows platform. So what it actually does is that it claims an IP address from your local network, usually through your DHCP server, and all the traffic going to that extra IP address is sent for processing to the NOAA core, to the core of honeypots we run and maintain. So virtually, attacker thinks that communicates with your Honey at Home clients, thinks that attacks your home computer, but in reality communicates with a set of honeypots that we run and maintain in the NOAA core. So this is some actual screenshots from the installation process of the tool for the Windows version. And it's a very simple tool, and after a few steps, it can start running. So these are screenshots from the runtime of the tool, and it starts running at the background. It creates a virtual interface, and then it asks for an unused IP address. So the local DHCP server gives an IP address back to the tool. This is step 3. So all the traffic going to that IP address in the last step is forwarded to our honeypots. So, as I said before, the usual way for Honey at Home tool to claim an extra IP address is through the DHCP server, but it also has a possibility to assign a static IP address to monitor and forward traffic for it. Also, for more advanced users, it supports BPF filters, so you can use Honey at Home to monitor and forward traffic for larger network blocks. It also does NAT detection and automatic port forwarding. This is mostly a feature for home users that are behind DSL lines or cable lines or NAT environments. And also, it has standard feature like automatic updates and some eye candies for the users. Some screenshots are here. For example, this is a protocol breakdown for the traffic received by the client, the top 10 TCP ports, or the traffic received and sent by the client over time. In the bottom part of the screenshot, we can see the actions that this client does. So it creates an interface, it sends a DHCP request, and gets an offer back. So an often question is that most users have only one IP address, and it's very unlikely that we'll get an extra IP address from their environment. And what can you do for these users? Such, for example, the old dial-up or cable users cannot claim an extra IP address from their ISP. So an experimental feature that we try to embed into the Honey at Home client is to monitor the unused port space. The fact that motivates us is that users are unlikely to run servers. For example, not any user can run Apache server or MySQL database in their home machine. So we can select a set of ports and monitor those ports until they get bound by the user itself. So if the user, for example, decides to run an Apache web server, we stop the monitoring for this port and we simply forget it. So this is an overview of the backend architecture of Honey at Home. We have the Honey at Home client, which forwards all traffic back to the honeypot core, the NOAA core. We actually run a HoneyD instance, which handles all the incoming clients, filters out any uninteresting traffic like incomplete scans and incomplete connections. And every established connection is forwarded to high interaction honeypots, and more specifically, we run the Argos system. Argos is an instrumented virtual machine based on the Argos on the QEMU emulator, and is developed by Priori University. A good property of Argos is that cannot be infected by remote exploits, simply because it is able to detect that code coming from the network is given to CPU for execution, and if such a thing happens, then the program itself stops its execution, gets killed, and restarted. So, as we want Honey at Home to be used by any user, and that includes even attackers, there are some challenges behind our approach. And one challenge is that we cannot trust our clients, as every attacker can install Honey at Home and misuse it. There is no level of trust between us and the users. So we have to hide both the addresses of our honeypots and the addresses of our clients. If the Honey at Home clients are known, then attackers can simply blacklist them, and we become blind to any incoming attacks. Also, the addresses of our honeypots must remain as hidden as possible, because we don't want to become victims of direct attacks or even blacklist our space. And a final challenge is that, as we know, that attackers run botnets and they have several thousands of machines under their control. So we don't want to have an incident when an attacker takes Honey at Home, deploys to thousands of machines concurrently, and all these instances starts running at the same time and flood our network with junk traffic. So in order to hide the identity of our honeypots and the clients, we use an anonymous communication system, and more specifically, the Tor system, which is based on the onion routing. So onion routing is a good technique that prevents several known attacks in the area of anonymization, like eavesdropping attacks and man-in-the-middle attacks. So it's based on a set of routers that forward the traffic for you, and even one or more routers in your path between the client and the server is compromised, privacy can be preserved. So we used Tors that provides both client-side and server-side anonymity, so clients do not know where they connect to because of a double anonymity path. And for automatic installation, so we prevent mass installation of mock-up clients. We used techniques like ones deployed by large sites like Hotmail and Yahoo and Google that are called CAPTCHAs. So we put a puzzle on each client. So every Honey at Home client has to be registered, solve this puzzle, and then each client can be up and running and connect to our core. We do not run the simple versions of CAPTCHA, which are based on static images, for several reasons. We have implemented our own version of CAPTCHAs. We call them enhancing CAPTCHAs, which is basically a mini application. So it involves some interaction with the user. So in this image, we can see an overview of our implementation, where these icons are spinning around the screen, and we say to the user, click on the apple or the tiger to continue with your registration. This is a simple measure to prevent what we call laundry attacks. So this is not a static puzzle like an image, and attackers cannot take our puzzle, forward it to their sites, and have users solve them for them. And you can find our tool, test it, install it make it cross in our website at honey@home.org. You can download all versions of clients. You can register there and read the documentation. And for those who are running honey@home clients, we have built sites where each client can view its statistics. So you just enter to the My Honey@home section of the site. You enter the ID of your client, and you see some breakdown of what happened to your client, what traffic it received, what traffic it sent, both in terms of what source IP addresses contacted my client and what destination ports they were looking for, and also the transport protocol breakdown. So to sum up, Honey@home is a very easy and lightweight way to set up a virtual honeypot to nearly every home PC. So you just download it, install it, and run it. And there's no cost either in the runtime or for maintenance purposes. And the two main challenges we faced is that we want to protect both the identity of users and honeypots, and that we want to prevent massive installations of our tool. So you can find it at honey@home.org, and we are open for any comments, requests, bug reports, future requests, everything you want.
Since you send all the traffic through the Tor network and to your own honeypot, actually, aren't you afraid that attackers can guess that the client is part of the honeypot based on the latency that is introduced in the system by comparing it to another IPs in the same subnet or something like that?
Yes, there are some timing issues when you use not only Tor but any anonymization network, because it's another layer in your architecture and imposes some delay. But what we have found is that there's a gray area. We have done several tests with home users, and that we know that they do not run Honey@home client. And we have seen that they respond very slowly for various reasons. For example, if you download a file from a peer-to-peer network and you consume most of your bandwidth, then your machine starts responding very slowly because you have taken all your bandwidth. And 30% of the clients, of the home users we tested, responded very slowly to some ports, although they didn't run Honey@home. So it's a confusing area. So you don't know if a home user consumes all its bandwidth, for example, to do a download, a web transfer, a peer-to-peer transfer, or it's a communication through Tor for Honey@home purposes.
Thank you. Any other questions? Okay, if there are no more questions, let's thank our speakers. Let me now call Stefano Zannero from Politecnico di Milano. Stefano graduated from Politecnico di Milano. He's a postdoc there, and today he's going to talk about anomaly detection and honeypots.
Yeah, thanks. Good afternoon, everyone. Well, actually, I don't know if you have ever had the feeling of shooting yourself in your foot. That's exactly the feeling that I had after giving in the title for this presentation when I was invited to speak here. Let me show you why. The idea is basically summed up in this slide. So, an intrusion detector, as probably anybody in this room knows, is a system which is built to detect security violation on an information system that is used for something else. So basically you have the usual distinction between host-based and network-based systems, so depending on the source of data you are analyzing. And more importantly to my talk today, you have the distinction between misuse-based detectors that are detectors that use and rely on signatures, and anomaly-based detectors, which are basically the thing that I've dedicated my academic life to study. So I'm one of those unfortunate persons trying to actually create an anomaly detector that works. On the other hand, an honeypot is a system which has value if it is compromised. So it's an information system whose only job is to get compromised. So you can very well say that an honeypot in itself is an anomaly-based intrusion detection system, in the sense that anything that happens on an honeypot is anomalous, and so it's an attack. But this is pretty different from what usually anomaly detection is about. Usually what happens is, except if you are operating in an environment such as the one NOAA has been studying, or such as the one Leurecom has been studying, that you have a system that you will go and study through basically a forensic approach. So after an intrusion, you will disconnect the system, you will analyze it by hand, and discover what happened. It's pretty much the point of having an honeypot, at least until 2 or 3 years ago. So, traditionally, what's the relationship between intrusion detectors and honeypots? Well, since intrusion detection systems, usually the ones you may have deployed on your networks, or the ones that you may have in fact seen in the commercial world, are misuse-based systems. There are basically known, and with a few exceptions, there are no commercially available, widely deployed anomaly-based detectors. There are just two exceptions of widely deployed anomaly-based detectors. One in the network arena, which is Arbor Networks technology, which is deployed by many carriers at the backbone level, but it's useful for detecting very wide variations, such as worms propagating, or viruses, or massive exploits, and this type of stuff. And on the host-based side, the only effectively commercially successful anomaly detector was the Okina Protector, which is then become the Cisco security agent. So these are the two commercially available anomaly detectors. Usually, if you think of an intrusion detection system, if you speak about an intrusion detection system, those that are hearing you think of a misuse detector. So think of a system which detects attack based on signatures. So it detects known attacks. If you think of misuse-based detectors, an intrusion detection system on a honeypot is substantially useless. The only use that you have for a misuse-based system on a honeypot is to use it as a logger to see what's happening, so to see the attacks that you already know about that are targeting your honeypot, or to use it as part of the honey wall for containment, so to avoid the attacker to use your honeypot to attack someone else. These are the two main uses of misuse detectors in honeypots. This is also because we deploy honeypots and honeyNets to try to get a grasp on zero-day attacks, on new types of attacks, on new types of behaviors. And by definition, these new types of behaviors are not captured by signatures. Otherwise, we would be just using intrusion detection systems instead. So the core idea that I'm trying to push to you is that misuse detectors in today's ONINET installations are basically useless. They are useful for doing a couple of things, but they are useless in the large sense. On the other hand, any anomaly-based system that you can think of is based on the concept of separating normality from probable or likely attacks. Well, on honeyNets, it's easy to conceive an anomaly detection system. Anything different than 0 is anomalous. So, basically, if I have proven that misuse detectors and anomaly detectors are both useless in the honeypot context, this is the end of my talk. I've given you the idea of what intrusion detection systems have to do with honeypots. So this is the point where I thought about I was shooting myself in my foot. Actually, that's not really what the end of my talk. There's a couple of lessons that can be learned from anomaly detection and that can be applied to the context of honeyNet. Anomaly detectors basically have 3 key features that can be used in the context of honeypot research. The first key feature is the ability of detecting outliers, so of detecting something different than normal. Well, in honeypots, what's normal is not the normal behavior and what's abnormal are the attacks. But in honeypots, everything is an attack. But what we are most interested into are attacks that are different from the normality of what we see. The internet today is so noisy and there's such a high volume of automatic attacks that we are not really interested into, that an anomaly detector can actually be used not to separate attacks from normal behavior, but to separate exceptional attacks from common attacks. The other things that it's useful and that can be brought from the anomaly detection domain to the honeypot domain is the idea of using some of the modeling techniques we use in anomaly detection in order to create, to capture, instead of capturing models of normal behavior, to capture general models of some types of attacks. So to perform some large-scale matching of attacks. And the third thing that I think can be drawn from the word that I'm more used to, which is the word of anomaly detection, to the word of honeyNet, is the idea of using basically clustering techniques applied to behaviors of programs in order to create, instead of using them to detect abnormal execution of programs, which is what we use them for in anomaly detection, they can be used to try to create aggregations, behavioral aggregations of types of malware. This is an existing example, which is Leurecom. Leurecom is a network operated by Institute Eurecom. It's a large network of honeypots covering more than 30 countries. It's a project which the Politecnico has participated in, Fort has participated in, a number of academic and industrial institutions have deployed their honeypots. This has created basically a large repository of attack traces. So what was particularly cool about this data set is the fact that everything was pushed together into a single database and could be queried. So on this data set, Mark, which is sitting there, and this group discovered and published several algorithms that in their case are click-based that can discover interesting attack patterns over a broad group of honeypots. This is the type of algorithm that I was referring to when I was saying that the same type of algorithms that can be used to find out anomalous events over normal events in a common information systems can be used to find out extremely anomalous or egregiously anomalous events inside a set of normal events in a honeynet. So one thing that we are currently working on is basically the following. We have been developing, well, actually I've been developing for years a network anomaly detector which is named Ulisse, which means unsupervised learning with a two-stage engine for substantially. So it's basically a system where, among other things, we have developed a way to use self-organizing map to sensibly cluster TCP and UDP packet payloads. Basically, the idea there is to use self-organizing maps to be able to distinguish among packets that belong to different protocols, which is easy, and to be able to automatically infer which packets are anomalous with respect to some characteristics that are shared by all the other packets that belong to the same protocol. The application that we are trying to do is to use the same algorithms that Ulisse uses to aggregate packets from various protocols and to find kind of generic signatures for types of protocols, to apply the same techniques to find generic signatures for traffic that comes, for instance, from scanners. If you have traffic that is coming from various types of scanners, that's pretty much something that you want to filter out from the whole raw data that you're looking at, or that you want to cluster together and forget about it, basically. So that's one thing that can be done using the same algorithms that are used for intrusion detection. On the other side of the world, so in the host-based systems, basically, this is another project that we developed, which is called SAID, which is basically an anomaly detector that uses system calls, sequences, and system call arguments. In this case, what we do is basically something that is quite complicated but can be summarized as I summarize it on this slide. You have a more or less classic Markovian model of the sequence of system calls. The only difference from whatever was available in the literature on this topic before SAID is that instead of using the system calls themselves, we are using clusters, or better, subclusters of the system calls that have parameters that are similar. So we use basically clustering techniques over the parameters to distinguish between different types of uses of the same system call. Because if you think about system calls, for instance, in a Unix environment, you think about the open system call. It constitutes like 18 to 90% of the system calls that you can find in some types of processes. It depends on the process, clearly, but in some processes it constitutes a huge volume of the system calls, and it's used basically for everything. So you have to find a way not to have one huge node in your Markovian chain where everything goes, because most of the times the system call is open. You have to find a way to disaggregate this in the various types of uses of open. This in the anomaly detection side is done to avoid mimicry attacks, basically, to make the model more sensitive. On the other hand, what we are doing, basically, is to use the Markov model of a specific application to check if the instances of that application that are running are behaving like as we expect them to behave. On the other hand, what we actually pretty much discovered while thinking about this topic is that you can use the same method in the, basically using it in the opposite direction to automatically cluster executions of unknown applications into similar sets. This can be done in a number of ways. Actually, what we did was to take out the result of one of our previous researches, where basically we built a model for a mechanism for generating an adequate number of Markovian models of behavior from a set of observation. In that case, the observation were commands, not system calls, but the mathematical concepts applies exactly in the same way here. Basically, the whole problem here is that you have a number of observations. These observations are generated by an a priori unknown number of models, and you want to generate a set of models that can explain those observations. If you do this by generating Markovian models, basically the problem is that you can generate as easily, if you have n observations, n Markovian models that model each single observation, or just one Markovian model that models all the observation. The only difference that you have is that the more general the model is, the less, lesser the final probability for each of the observation will be. So basically you have the opportunity of either creating a very general model that fits all the observation but somewhat loosely, or many very specific models. The mathematical problem is how do you automatically infer, or how do you automatically know where to stop? This is basically, well, in the slides it's explained with a little more of mathematical detail, but basically this is done by an appropriate choice of the prior of the decomposition of the Bayesian decomposition that you see over there. The problem is that this trick is not new. This trick is something that already appears in the literature. The problem is that usually when you use this trick, you are able to assign a prior, decomposing it depending to the complexity or to the type of model that you are parameterizing. And this is not feasible for the type of models we have. We don't have the a priori knowledge that we would need to apply this trick. So basically what we did was to apply another trick, which is, if you call it in a very, very academic way, it's a non-informative prior criterion, which basically means that you make up a prior which more or less works. It's not exactly like that, and mathematicians could kill me for saying that, but basically a non-informative prior is something that you make up and pray it works. We created this prior, which basically, besides the mathematical structure, says a very simple thing. It says you should try to use the same models that you have already been training, so you should try to fit one of the models that you already have, unless the benefit in creating a new model for fitting exactly this sequence is so large that it makes sense to add one more model. And playing with the constants of this prior, basically you can say how keen you are on creating new models and how instead you are conservative and you want models to be generalized. This actually, you have sort of some kind of control on how many models will be generated, but you don't have very fine-grained control on it. The only way to have very fine-grained control on it, and actually the only way to bypass the problem of the prior altogether, if you want, is to operate in a different way, which is the way suggested by Rabiner, which is to operate by merging. Basically, the idea here is that you create a set of models, even one for each single instance that you are trying to model, and then you try to merge the most similar ones until the merging step costs too much. It's another formulation of the same sentence. The problem is that the problem are twofold. The first problem is that you still have to set this threshold, how much you want the merging process to go on. But since it's a binary process, you can basically decide number of models or a reasonable number of models that you are willing to accept. The second problem, which is more troublesome, is that actually the the distance that Rabiner suggests for merging models, which is the one defined over there, which basically says that two models are, the distance between two models can be computed by generating a sequence, finding the probability of the sequence in one of the two models, finding the probability of the sequence in the other, and doing some maths or some composition of these two values, and depending on which type of composition you can get different types of distances. This is the one that Rabiner has defined, and which has some nice mathematical properties, but you can define others. The problem is that the heavy step here is in generating a number of candidate sequences and generating the probabilities for each. So basically, the problem is that if you try to do this fastly, you will find out that computing those distances is it's a computational intensive problem, not in the sense that calculating a singular value decomposition in computational intensive, but in a sense that is enough to make it unsuitable for real-time or near real-time detection. Basically, this is one of the things that can be that this type of models can be used for. So, for creating and clustering the behaviors of unknown different applications, so that similarly behaving applications are clustered together. On another note, in a recent work, we basically used SAID to detect and create an audit trail for in-memory injection of attack code. Basically, we used a number of techniques that are commonly used to create shell codes that can execute a new process inside the memory of another process without calling an exec system call. This is useful because in any type of architecture where you are monitoring what is being executed, actually, an attacker that knows that you are monitoring the execution of new processes can take advantage of this by avoiding to execute the execv system call or analogous system call for another system, and doing what is called a user-land exec. So basically executing the new process inside the old one, just like a small alien growing up from the old process. Well, this is, of course, of forensic use. On common machines, this is of purely forensic use. The fact that I can point you to is that if you actually happen to run a honeypot, you will see that what used to be a very unusual activity, so the honeypot would get compromised very rarely. It would even be contacted quite rarely. Today is a much more common thing. So honeypots receive a lot of noise, of activities that basically you are not very interested in sifting into. So an anomaly detector such as SAID can actually help in sifting through the forensic trails that you have already generated, because on a honeypot you don't need it to trigger the generation of the forensic trail. You are generating a forensic trail of everything. But you can use it to spot particularly interesting portion of the trail of events. So basically, this is the same concept that Marcus Ranum once defined as artificial ignorance as opposed to artificial intelligence. So you're not using filters to filter out things that are interesting, but you're using them to filter out things that are worth ignoring. This is exactly one of the ways that anomaly detectors can be of use on modern honeypot installations. So to ignore events that are repeated too many times and that are therefore less interesting. So, reaching to the conclusions of this talk, I've briefly shown how different lessons drawn from anomaly-based intrusion detection can be used in honeypot research activities. Basically related to three different things: finding interesting activities over a large volume of logs, creating models of attack behavior as opposed of at creating models of normal behavior, and creating taxonomies of attacks, or better, taxonomies of malware in our case, through behavioral analysis. This is, of course, a quick overview, which is more meant to raise questions that I will be happy to handle right now or to handle offline if you wish. So I'm providing more questions than answers, actually. And so the usual standard warning about forward-looking statements included in this presentation applies. So it may very well be that some or even all of the things that I've told you about will demonstrate themselves less useful than I think them to be. But you're more than welcome to tell me ahead and save me a lot of time trying to demonstrate if they are useful or not. So that's all. Thanks for all the questions that you may have. And you can reach me at that address over there. And if you, in any case, for any reason whatsoever, which I don't really understand which reason you could possibly have, if you want to download the byproducts of my doctoral thesis, Ulysses and SAID are available for download at those two addresses mentioned on the slide. Thanks.
So with respect to Ulysses, could you tell us how this approach is likely to work with respect to polymorphic worms or binary protocols where contents of packets may look differently?
Okay, the answer is in two parts. The first part is, with respect to binary protocols, it depends on the type of protocol. And the second part of the answer, which is the real answer that you probably wanted to get to, is if your payload that is interesting in some way is, for instance, encrypted. So if you have a very small encryptor before the actual content of the packet, and then you have basically random characters after that, then unless that specific thing on that specific network, which may very well be the case on a honeypot, unless on that specific network you have no protocols whatsoever that behave in a random or random-like way, it will probably get in the middle of the others, because of course the clustering part of Ulysses is looking at frequencies and relative frequencies of the distribution of characters. So if you show it something totally random, a totally random result will turn out. So that's pretty much the point where the blind spot, let's say, of the system.
I understand that you had a heuristic. Yes, I understand you have a heuristic in estimating a priori probabilities. Mm-hmm. Did you check that against data to see if...
Actually, it was published like 3 years ago. I don't know if there's a reference on the slides, but if you cannot find the reference, I can point you to it. And in that paper, we evaluated it on a real data set but it was a modeling of sequences of user commands in that particular data set. On the specific modeling of system calls, we have not validated it yet. But the mathematical game has been validated on a different data set.
And the second question has to do whether you run into state explosion kind of phenomena in your analysis.
No, not really, because the number of system calls is limited, and you basically in a portion of research that I wasn't able to show, which has to do with how SAID works, but it's documented in the papers describing SAID. Basically, you can tune very finely how many clusters you want to create for each system call. In general, what happens is that most system calls have so little executions in the context of each specific instance of the process that they get only one cluster. So basically what you have is an explosion, but just for those system calls that are too numerous to be modeled correctly. So the answer is, in general, no. There's no such problem, because you can control it very much as much as you want. So.
Any other questions? If there are no other questions, let's thank you.
Thanks.
Well, welcome everybody. I hope my talk isn't useless after the one of Stefano. Well, I think it isn't, but yeah, maybe. The outline of my presentation. First, I will show you some motivation for our work and the problem statement. And then I will show you the basic building blocks of a system for automated signature generation. And then the main part of the presentation will be about the approach for signature generation for the NOAA project. A recent study at the ETH Zurich has shown that the speed of insecurity is much faster than the speed of security, and we can see it on this graph, where we have on the x-axis the days from disclosure of a vulnerability, and on the vertical axis we have the corresponding cumulated probability for exploits and patches available. What we can see is that we have on the day where this vulnerability gets disclosed publicly, we have a very fast increase of both the probabilities for exploits and patches available. We can see that the probability for an available exploit is always higher than the corresponding availability for a patch. And we have, within a day after the day of disclosure of the vulnerability, about 90% likelihood that we have an exploit available. This time span of a day after the disclosure we call, or the exploits within this time span we call zero-day exploits. What can we do to defend against such zero-day attacks? One approach are intrusion detection systems. They usually separate benign and malicious network traffic and use some kind of signatures, mostly host or network-based signatures. The drawback of these signatures is that they are still mostly handcrafted, and this reactive generation of signatures is too slow for zero-day attacks. And so we have to find other options. We can see here the basic building blocks of a system for automated signature generation. We could have several sites that are able to detect attacks, either unknown or known attacks, and then the raw data of the attack is forwarded to an analysis engine which is able to extract some useful attack information about the attack in form of an attack vector. If we have several sites, we could correlate these vectors, and a signature generator will use the refined vector to transform the vector into a signature which can be used by, for instance, proprietary signature or intrusion detection systems. So the NOAA approach, first, what is actually NOAA, or at what aims NOAA? It aims at the automated detection of unknown attacks and the generation of signatures to counter zero-day attacks. Well, again, after your presentation, I'm not so sure about that. And the main goal is to generate signatures for common intrusion detection systems and to install a full-scale infrastructure across Europe which can be accessed by internet service providers and education networks and researchers. The attack detector in NOAA is called Argus, which is a honeypot system, and it uses a compromise-based detection technique called memory tainting. We can see on this illustration how this mainly works. We have a host operating system on top of which we have a hardware emulator running and some guest operating systems. Whenever we have some incoming network traffic, we will mark the network bytes in the memory as tainted, and if the CPU is about to execute or jump to addresses which contain tainted data, we will stop the execution and raise an alert. And this allows us to detect remotely injected code execution attacks with almost 100% accuracy by design. And the scope of NOAA are mainly remote attacks that do not require a human in the loop. The attack analysis is done by combining different analysis engines, which we call extractors. And each extractor is responsible for extracting information about the attack from a certain source. And the extractors can depend on each other. And for instance, this means if an extractor with a higher precedence fails, another extractor may not even work. All the extracted information will be collected into a meta signature, which describes the entire set of available attack information, and we can estimate the quality of such a signature by using the information about which extractor succeeded and the value and amount of extracted information. In our prototype implementation, we have combined host and network-based analysis. The first extractor uses host-based information or extracts host-based information from Argus. It identifies the memory content relevant for the attack. It identifies the operating system and the attacked process and the network traffic bytes involved in the attack with the help of this tainting technique. And the second extractor relies on the first one, and it extracts network-based information from a protocol state tracker, and it refines the information from the first tracker by adding protocol field information to the network bytes that are involved in the attack. Furthermore, we have protocol state information for the entire network communication related to the attack. Here we can see the basic architecture of the entire system. We have on top the honeypot system with Argus, which will recognize the attacks in the best cases, and it will inform the signature generator about the attack. Based on the alert information, the signature generator will start an extraction thread, which uses the first extractor for getting information from Argus, and then the second extractor will use information from the network protocol state tracker. All the information is collected in the meta signature and stored in a database. The network protocol state tracker tracks the connections towards one or more honeypots and logs the protocol states for each packet. User-defined packet and connection analysis is possible, and the tracker is highly configurable by relying on various libraries, which we'll see a slide later. And the state machines we have configured or for which we have provided specifications are IP, TCP, UDP, and FTP, just for a proof of concept case. The two main libraries the tracker relies on are the NetB library and the NetProto-FSM library. The NetB library is currently developed by the Net Group at Politecnico di Torino, and it provides components for different types of packet processing. We mainly implemented the packet decoding functionality and extended it slightly for our tracker. The second library we have implemented by ourselves, and it is an implementation for finite state machines for describing network protocols. Our approach is based on a work by J. van Gorp and J. Bosch, and it features protocol state machines that can be specified by XML files, and the implementation is resource gentle and more or less slim, and features are a flexible timer mechanism which can be used to schedule events or timeouts, and it is possible to implement custom actions for the specified transitions. We can see here on the left half of the illustration a basic architecture for the tracker. Unfortunately, I have no pointer, so forgive me for that. And first, we capture network packets with the PCAP library. And second, we use the NetB library for decode the packets and add packet field information. Out of this information, we will create some event data, which drives all the state machines for the entire protocol stack of the network packet. And for each transition that will be executed, we have some logging action implemented, which writes out state and field information into two log files. On the right half of the illustration, we can see a possible architecture for a replayer. Replaying is especially useful if you want to do some offline analysis of an attack. And you can see that we read in the information, the state or the connection history from the tracker log, and use a replayer to substitute all the fields that have to be adapted to the current test or offline analysis environment. We then again create event data and use our state machine to make the current state changes. And we will then execute some replaying actions which will send the packets over the network. And the responses, we can receive the responses from the replaying actions, and we can match them again against the expected responses from the tracker log file. Well, yeah, there is a context menu. Well, thanks. Here we can see all the components that are involved in the extraction of information about the attack. First, we have Argus that is able to detect an attack, and in this case, if tainted data is about to be executed, it will give us the network packet from which, or the network packets from which the tainted data originated. And the first extractor will then give us or determine the position of the tainted data in the network packet. Furthermore, it will add protocol field information, and the second extractor will add protocol state information for all the protocols contained in the network packet. And additionally, Argus will give us the name and of the operating system and the process attacked. The signature generation follows the following main flow. We first use the meta signature from the extraction part and determine the signature quality. Then we save it to a database and use adapters to create signatures for specific signature formats. We again can store, correlate, and or distribute the adapted signatures. In our prototype implementation, we have used Snort, or implemented an adapter for the Snort Signature format, because Snort is open source and well known, and the signature format is more or less simple. The drawbacks are, on the other hand, that we cannot use the full set of information that we are able to extract from an attack. Here we have an example of such a Snort signature for an FTP service exploit. We have on the upper part some basic information about the source and target addresses, the transport protocol, and the text message, which we have automatically created, and which describes the main characteristics of the exploit. At the lower part, we have first some connection state information that can be expressed in the Snort syntax. And most important, we have a rule that identifies or filters the packets for which a vulnerability has been detected and should be protected by this signature. This rule or the bases on the information that we use to trigger the state transitions in the tracker. Then, furthermore, we have the vulnerable fields of the application, which we have to protect. Yeah, and we can see here an example where we have a field that should be terminated by a certain token, and if this token won't occur within a certain range, then we have to raise an alert because there is some possible buffer overflow of a vulnerability. Yeah, possible buffer overflow vulnerability. So the conclusions are that our system generates signatures with nearly zero false positives. We had test runs against normal traffic, which never, and the signatures were never triggered. So this is a slide indicator, and this this statement is valid provided that we have remote code injection attacks that can be detected by Argus, and that we were able to extract the full amount of attack information. The signatures describe the vulnerability of an application and not just properties of an exploit that is observed. And so we are able to protect the server applications from buffer overflows in arbitrary protocols and fields. And due to this, our signatures can compete with other approaches, provided that we have the above conditions met. Well, yeah. Thanks for your attention, and if you have any questions, you can ask me.
Jan Mels from Åbo Academy University. Do you make your signatures available for the public?
Well, they are available first for test scenarios as a part of the EU project NOAA, where we will test it in a full scale environment, in a real test scenario.
I will sit at the back next time. So if I understand correctly, Argus is stopping the connection when it detects a code injection, right? And so basically what you see in the byte stream is the shell code, right? And today most of these shell codes actually are packed with one technique or another. That means the bytes of stream is always different. So what's the usefulness of creating signatures for something like that?
Well, the point is not the information or the information locked. We just use the information that we get from the memory dump and so on for analyzing the attack. And out of this information, we have we can get the vulnerability of the application. If this is an answer for your question, I'm not sure. Yeah, okay. That's